Hello everyone. Can you hear me?
네, 잘 들립니다.
Yeah, thank you. So actually this is the third class of this course, but I missed the second class. So I recorded the lecture video and posted the recorded video on YouTube. So actually, we are learning about the storage system, and then as you know, this storage system is actually the bottom part of the memory hierarchy. So actually, so my research area is computer architecture, and then traditionally the computer architecture research just handled until the main memory, because so usually the computer hardware handles until the main memory. So actually, storage system is also hardware. So because it's a kind of the memory devices. So sometimes this storage system is called the secondary memory. Okay. Yeah, but the storage system, actually the performance of a storage system is much lower than the performance of a main memory. So if the performance is low, then these devices are handled by software, not hardware. Because the performance of hardware is much higher than the software, but the disadvantage of hardware is that we cannot configure the hardware. So that means if the hardware is fixed, then we cannot modify it's very hard. So it's not easy to modify this hardware system. So usually, and then also the hardware focused on the common case. That means that so frequently used part. So but this storage system and IO devices are, and then also network is very slow compared to the CPU or some main memory. So these parts are handled by software, usually operating system. But the operating system directly handles these devices. So actually, the hardware vendors make the device drivers, and then operating system control these device drivers. Okay. Sorry. So in the previous class, I briefly covered how IO devices are controlled by operating system. So, actually, I start from these IO devices because traditionally, I mean, traditionally, this storage devices, performance of storage devices is so very low. Usually, these storage devices are controlled by operating system like IO devices. So as you can see, so this is the old computer system architecture. It's not modern computer. So it's not current computer system architecture. So as you can see, the storage devices are located the bottom of the hierarchy here. And then also multiple storage devices are connected to common IO bus. So that means that the hardware resources of this common IO bus is shared by multiple storage devices, but it's enough. So because the performance is so low, but this is the architecture of the modern computer system. And then as you can see, the nose bridge part is integrated into the CPU chip. And then this is one CPU chip handles the main memory and GPU directly, because the required data bandwidth for main memory and the GPUs are very high. So these devices are handled directly by CPU, and then also the storage devices, other I/O devices like keyboard and mouse and network, sorry, are connected to the point-to-point communication chip. So actually, this chip is called the mainboard chip, and then traditionally this chip is called the Southbridge chip. But as you can see, the SSD can be directly connected to the CPU. That's a modern CPU here, because recently the size of the data is very large, and then also the required data bandwidth from the storage is also very high compared to the traditional storage system. So these SSDs are also is being included in the mainstream of the computer architecture. That's why, because we require the high performance of storage system recently. So in the previous class, we also learned about the typical I/O device architecture like this. So typical I/O devices are composed of hardware interface such as the communication media, for example, the SATA or PCIe. Then these devices have some control registers and then data registers for data transfers. And then if the operating system, so when the operating system and actually the device driver update some part of this control registers or data registers, then command is delivered to these I/O devices. So actually this is the hardware, but most of control is handled by software called firmware, and then also the I/O devices has its own hardware, so like a CPU, like or microcontroller, memory system like DRAM or as cache, SRAM, and then other hardware chips. So this system software runs on its own system. I call this its own system, the system of the I/O device, and then this firmware was controlled these devices, hardware of the I/O device. Okay. So, and then so today we will cover the two typical, that means that widely used storage devices. The first device is the hard disk drive. That is the traditional storage device. So hard disk drives are traditionally widely used storage system. So firstly, we will cover how the hard disk drives work in the computer system, and then we will cover the basic architecture of SSD. That means solid state drives. Okay. Okay. Let's start from the hard disk drive. So, as you know, this hard disk drive is located at the bottom of the memory hierarchy. So that means the performance of a hard disk drive is much lower than the other higher level of the memories, such as SRAM or DRAMs. But the cost is very low. So that is the main feature of each level of the memory hierarchy. So if the level is low, then that means that the cost is very low. That means the density is high. So we can store the large amount of data, the user data, on storage devices such as hard disk drive. So we already know that recently we used a very large size of hard disk drive, something like 1 terabyte or 2 terabyte, even 4 terabyte. And then if we run network attached storage system called NAS. Then the the size of the attached hard disk drive is much larger than the conventional personal hard disk drives. Okay, but this hard disk drive is a physical devices. Oops. Okay. So that means it's not a perfect memory system. So this device may have errors, also bad blocks. Also, the seek will take a long time because this is the mechanical drive. So actually the operating system gives some control signals to the hard disk drive, such as read, write, or erase. It's a very simple command. But inside of the hard disk drive, because the hard disk drive is not a perfect memory device, so this hard disk drive receives these control signals, and then the software, that means the firmware of the hard disk drive, need to manage the storage media of the hard disk drive. Okay, so because this is not a perfect memory system, so actually the inside of the hard disk drive, the operation is not simple. Okay, the hard disk drive would need to manage the request from the operating system, but the inside of the hard disk drive is not simple. So we need to hide this mess from the higher level software. So this is the abstraction. This is abstraction. So if the abstraction level is high, this level does not consider these messy jobs. So that means the complex jobs. So these complex tasks are hidden from the low level. So low level just provides some interface signals and the response from the high level. Okay, but inside of the in the low level, we need to control or manage some messy jobs inside of this storage system. Okay, so let's see the architecture of the hard disk drive. So actually the hard disk drive is the mechanical drive, not solid state drive. So actually SSD is the solid state drive. So that means the hard disk drive is composed of some mechanical parts, because the data is stored on the surface of the platters. So data is stored in the surface of the platters. And then by changing the status of magnetic status. So that means that actually the hard disk drive encodes and decodes the magnetic signals on the surface. Then these magnetic signals are actually the magnetic status is stored on the surface of these platters. Okay, so actually these platters are main storage media of hard disk drives. So these magnetic signal states should be read by some devices. So these platters rotate inside of the hard disk drive, and then as you can see, there is a spindle motor. This spindle motor rotates the multiple platters. Okay, and then hard disk has the actuator and then arm, and then on the end of the top of the arm, there is a head. So actually data is read by this head, and then the actuator and the arm is used for seeking the target block. That means for read and write. So these actuator and ARM are used for seeking the location of the target block in this platter. And then hard disk drive also has its own interface to the host system. So you can use the SATA or SCSI interface for this hard disk drive. And then in order to control the data transfers, and then also this in order to control some actuator arms and spindle motors, also the data transfers, the hard disk drive has its own microcontroller or some storage processors. And then for this data transfer, the hard disk drive has also buffers. Okay. And then let's go deeper into the media, the storage media of the hard disk drive. So actually, we can find the hierarchy, the architectural hierarchy inside of this storage media of hard disk drive. So these are components of a hard disk drive: the platters, surface tracks, sectors, cylinders, and arms and head. Actually, but in this component, arm and heads are used for seeking the target block inside of the hard disk drive. That means the platter. So these are the mechanical part. Also, cylinders are also mechanical part, not the part of the storage medium. So these are the mechanical part. But in the storage, so on the storage medium, so let's see the storage media of the hard disk drive. So we can divide the this storage media as the platters, surface, track, and sectors. So what is the platter? So platter is the very it's kind of a circular platter. it looks like a dish, very shallow dish. Okay, so platter is just a plate, a circular plate. So actually, inside of the hard disk drive, the hard disk drive can have multiple platters. So that means the data can be stored in some one of these multiple platters. Okay, and then as you can see, this platter is the circular plate. There are two surfaces on each platter, right? The front surface, and then the back surface. So actually, the data is stored on the surface on the plate. So there are actually two sides on this plate. So inside of the platter, inside of our platter, there can be multiple surfaces, but usually two surfaces. Actually, two surfaces, not usually, actually two surfaces. And then if we see the one surface, then we can divide a surface into multiple tracks. So tracks is some circular, how can I say? It's a linearly circular line inside on the surface. And then as you can see, we can divide this single surface into the multiple tracks. So it looks like a thread on the stadium. So, okay, if there are multiple tracks on the stadium, then only one person can run in on each track. And then it's same to the hard disk drive. So data can be stored in the each track. Okay. And then this stack track is divided into the multiple sectors. So we divide the each track like a multiple part like this. So this is a sector. So the data is stored in the actually the in a sector of a hard disk drive, and then it is so like this. So the location of the data, the location of the physical location of the target data can be represented by a platter, a platter and a surface, track, and sectors. So like the first platter, and then front surface, and then track number 10, and then on this track, and the sector number 5, like this. So we can represent the location of the target block like this. But the software side, this is the physical side. So on the software side, these track, well, no, these sectors are represented as the blocks, so block number. So actually the operating system gives the target block for read, write, or erase, and then the hard disk drive receives that is a control signals, and then block number like logical block, and this block number is called the logical block address. And so hard disk drive receives that is logical block address from the operating system, and then translate this information into the this component part, like platter, surfaces, tracks, and sectors. And then hard disk drive control the, actually the cylinder is the, so it's the some cylinder that rotates the multiple surfaces. So multiple surfaces are connected to one cylinder, and then this cylinder is rotated by motor, so spindle motor, and then the hard disk drive will control the location of the arm, and then actually head is located on the end of the this arm, and then hard disk drive control this actuator. So this arm is moves like this. Okay, so arm moves like this. So the arm can access the from outer track to the inner track like this, and then this actually the hard disk drive is a rotate. The platers rotate, so we can approach the actually the head of the arm can access the target sector when the rotated track is rotated track approach the head of the arm. Okay, so these are mechanical part, and then this is the some structural hierarchy, architectural hierarchy of the hard disk's storage media. Okay. That's what I already explained. So disk is composed of platters and surfaces, and then each surface is divided into multiple tracks. It's a circular ring, and then each track has divided into sectors separated by gaps. So this is so sector is the basic access unit in the hard disk drive. So there can be multiple platters, and each platter has two surfaces, okay, like this. Okay, then how can we calculate the capacity? capacity of the hard disk drive. So hard disk drive is the storage devices. That means that the user data is stored in the inside of the hard disk drive. So actually this user data is recorded, so stored on the surface of the hard disk drive. So how can we calculate the size of the, that means the size of the hard disk drive, that means the capacity of the hard disk drive. So we already know that the computer system is the digital system, so data is stored like stored as the binary data. So each data has 0 and 1. So that means the the, the bit data is recorded on the hard disk drive. So capacity means the maximum number of bits that can be stored inside of the hard disk drive. And then this capacity of the hard disk drive is determined by the recording density. So that means the bits per inch. So as you can see, each track is divided into each track is divided into multiple sectors. So if we just focus on this single sector, then you can see this single sector has a linear form. So actually, the data is recorded on a single sector linearly like this. Yes. So I said the hard disk drive is the magnetic drive. So that means the magnetic signal states on this sector is changed. So actually, each bit is linearly recorded on the surface of the hard disk drive. Okay, so the recording density means that it's the unit of the recording density is bits per inch. So it's an inch. So that means the number of bits that can be stored in 1 inch length. Okay, it's because the data is recorded linearly on a single sector. And then track density. So a single surface also can be divided into multiple circular tracks. And then each track has a width, its own width. Okay, so actually the size of this platter, that means the radius of the platter is it's a fixed size, the fixed width, the radius of this platter. But then we can divide this surface into multiple tracks by the width of a single track. So the track density is defined as the number of tracks per inch. So that means the number of tracks that can be squeezed into 1 inch radial segment. So that means the number of tracks in the 1 inch length of the radius. And then based on this recording density and track density, we can calculate the areal density. That means the bits per square inch. So that means unit area. So that means the number of bits that can be stored in the unit area. So and then this areal density is determined by recording density and track density like this. But on the traditional hard disk drive, that means we divide the track. So that means each track has the same number of sectors. So what does that mean? That means we just divide tracks like this. So each track has the same number of sectors, but the hard disk, the plate of the hard disk drive is a circle, has a circular form. So, but as you can see, the inner track has higher recording density. So that means this should with this short line of the sector, so short width of the sector, let us assume that 1,000 bits are recorded, but on the outer track, as you can see, this length of the sector is longer than the length of the inner track. So on the outer track, the same number of bits, like 1,000 bits, is stored in the longer sector. So this is the traditional hard disk drive, but the disadvantage of this this structure is that, so as you can see, the recording density is higher for the inner track, but the recording density is lower for the outer track. Okay, so the modern hard disk drive divide the tracks into multiple zone. So actually, in each zone has the different number of sectors. Like so, in an inner zone has divide the sector like this, but in the outer zone we also divide multiple sectors. The more sectors, the outer zone can have more sectors. Okay, so modern hard disk drive has multiple zones, and then so there each the tracks of the hard disk drive may have the different number of sectors. Oh, we can easily calculate the capacity of the hard disk drive based on the structure of this hard disk platter. That means the structure of storage media of hard disk drive. So if we know the number of platters and then number of surfaces, tracks per surface, and number of sectors per track, then we can easily calculate the total capacity of hard disk drive, like this equation. So number of bytes per sec, the average number of sectors. This is average because there can be multiple zones inside of the hard disk drive. So average number of sectors per track, number of tracks per surface, and like this. And then obviously we can use this equation. So in this example, the sector size is the 512 bytes, and then there are 300 sectors per track on average, and then 20K tracks per surface, 2 surfaces per player, 5 platters. Then capacitor is calculated like this, just multiply. Also, we will learn about this some architectural hierarchy of the storage media in the SSD, because the flash memory is also divided into multiple hierarchies, storage hierarchies. Also, that is the same to the main memory, because as you can see, the DRAM is DRAM. Actually, we use the DIMMs. And as you know, the DIMM has multiple DRAM chips, and then also DIMM has the ranks. That means the surface of the different surface of these DIMMs. Also, inside of the DRAM chip, each DRAM chip has multiple banks. And then multiple banks, and the one bank has multiple rows and columns. And then based on these numbers, we can calculate the capacity of the single DIMM. And it's the same to the hard disk drive. Also, it's the same to the SSD, the flash memory. So we will learn about the flash memory also today. Then actually, based on some architectural hierarchy of the storage media of the hard disk drive, we can calculate the capacity of the hard disk drive like this. And then this slide shows how the hard disk drive read the data on the target sector. Okay, but I already explained how the hard disk drive read the data. Okay, so actually the hard disk drive is the mechanical drive. So this platter rotates in the same direction. So actually the hard disk drive rotates. The spindle motor rotates the platter of the hard disk drive at the fixed rate, fixed rotational rate. And then this is the actuator, and then arm is connected to the actuator. And then on the top, in the end of the arm, there is a head. So actually the data is read by this. The data is only accessed by the head on the top, on the end of the arm. So, and then the another end of the arm is fixed in the actuator. So this actuator controls the location of the arm, like here, here, here. But as you can see, another end of this arm is fixed in this location. So the arm moves like this. But as the platter rotates in the same direction, then we can the head of arm can access some target sector, target track. So by moving the location of the arm by actuator, so like this, the head of arm is moved to the target track. Okay, so as you can see, if we move the arm like this, then the head of the arm can move to this track number, and it's track number 0, track number 1, track number 2. This arm or the head can approach to the track number 2. Then how? So let us assume that the target sector is here. Then how can you access this target sector? But this platter rotates in the one direction, and then the head waits until the target sector approach to this location of the head. And then if the sector is here, then the head can read data on the sector. Or we can also write the data on the target sector. Also, we can erase the data on the target sector also. Okay, that's how the hard disk drive works. So, as you can see, this is not simple. Because this is the mechanical drive. It's not simple to access the target sector. What that means, the target block of the data. So in order to access the target sector, then we need to control the location of the arm, and then this arm moves to the target track, and then wait until the target target sector approach to the head of the arm. So it's not easy. Also, it will take a very long time. And also, another problem is that the access latency is not constant. So based on the location of the target sector, this is the head need to approach to the target sector, and then based on the location of the target sector, this seek time, it is called seek time, and then seek time is different based on the location of the head, also the location of the sector, target sector. And then seek time varies. Seek time varies inside of hard disk drive. So it's not easy to control the hard disk drive actually. So let's think about the DRAM. So it's a memory. So DRAM is it's actually the semiconductor devices. So solid state chip. Okay. So DRAM has also a different latency for the low heat or some tank conflict, but usually this difference is not large. So then we can access the data inside of the DRAM within some constant latency, and that also is fast because it's not mechanical. So we can just access the location of the DRAM using some electric signal. And electric signal is much faster than the movement of the mechanical devices. But hard disk drive, hard disk drives have a mechanical part, and then because of this mechanical part, the latency of the hard disk drive is much slow, like millisecond latency, multiple milliseconds. Okay. So let's see the details of operation of this hard disk storage media, like platters. So actually there are multiple platters and then one cylinder. So actually the multiple platters are attached to a single cylinder, and then this single cylinder is rotated by single spindle motor. So that means that there are multiple platters. Multiple platters rotate simultaneous. Multiple platters rotate at the same speed, and then the arm is connected to the surface, each surface of the platters. But as you can see, multiple arm, the arm has also multiple heads, and then this number of heads is same to the total number of surfaces inside of the hard disk drive. So as you can see, each head is connected to is assigned to each surface of hard disk drive. So, and then as you can see here, you can find the multiple heads here. And then also these arms are connected to a single how can I say single arm like this. So when a disk, that means a platter, rotates, each head is actually each head is actually accessing the same location of each surface. Okay, in unison. So that's what I already explained, the track and sectors. So, and then let's see how the head access the target sector. So I had the input of a track here, and then the disk, that means the platter, rotate in the same direction, and then let us assume that this is the target sector, and then the head of this arm with the data on this blue sector here. And then, so now this head, this head with the data on this blue sector here. Then let us assume that the next target sector is this red sector. So as you can see, the red sector is located in the outer track of this surface. And so this request is given to the hard disk drive from operating system. So then the first and so actually this in this slide it looks like the location of this arrow is moved to the behind of this hard disk drive, but actually it moves like this here because this arm is connected to the actuator like this. So first this arm moves to the outer track, and then the track rotate, and then the head is located the beginning of this sector, then the head starts to read data on this sector, and then it's done. So this is the read. So we can divide the access latency, that means the access time for hard disk drive, into the seek time and then rotational latency, because the seek time means that we just move the location of the head of the arm to the target track, and then this head needs until the target sector is located on this head. So we need also consider the rotational latency, and then also data transfer takes time. So we need to also consider the data transfer time on each sector. So this is the disk access time. So disk access time, the hard disk access time is composed of this seek time, and then rotation time and transfer time. Okay. The seek time is that the seek time includes this move the head of the arm to the target sector. So we need to control this actuator. and then this seek time is also consumed by moving the arm and then the location of the head. So actually the seek time is on average 3 to 9 milliseconds. It's very long. The seek time is very high, and then rotational latency. And then when the head of arm is located at the beginning of the sector, then we can read the data. Okay. So this average rotation time is determined by the rotation speed of the hard disk drive, like RPM of the hard disk drive. So we can easily calculate this rotation time, average rotation time like this. So, and then RPM is number of rotation per minute. So if you see the specification of, if you read the specification of the hard disk drive, then we can easily get the typical rotation time and transfer time. This is the time for reading a bit in the target sector. So transfer time is calculated like this. So this example shows how we can calculate the data access time in the hard disk drive. So this is the rotation rate is the 72K RPM, 7,200 RPM, and then average seek time is 9 milliseconds, and average number of sectors per track is 400. So rotation is that. So first, so this is the average rotation time. So we don't know where is the target sector. So when the head is approached to the target track, and we don't know where is the target sector. The target sector can be found here, or target sector can be found here. So the target sector can be found here. If target sector is here, and then if the disk rotate in this direction, then we need to the hard disk drive wait very long time until it's here. But if the target sector is here, then this hard disk drive can read the data on the target sector quickly. But we don't know the location of the target sector on the target track. So we just calculate the average rotation like this here, 4 milliseconds. So the average, and then also in order to read the data on this target sector, then we divide the one track into 400 sectors, and then we also calculate the data transfer time. That means the time for reading a data on the target sector, like here, is 0.02 milliseconds, and then seek time. So actually, usually the seek time is given because we don't know where the hard disk. Also, the location of the head of the hard disk drive. So it's a 9 milliseconds. So usually, also this rotation time may have some also take some time for this access time. But as you can see, this seek time is occupies the large portion of the access time. So actually data transfer time is very short because the one thread can have a large number of sectors. So actually the rotation time for this amount of length is very short. compared to the rotation time for the half half of the this track length. Okay. So this is the total access time of the hard disk drive. Then, as you can see, the seek time occupies a large portion of the hard data access time of the hard disk drive. Also, but we cannot change this rotation time. This rotation time is determined by the rotation speed of the hard disk drive. So if we increase this rotation speed, then we can also reduce this time and this time, right? But if the rotation speed is fixed, then we cannot change this rotation time. Rotation time and data transfer time. But the seek time is determined by the location of head and target sectors. Okay. So this seek time can be changed by scheduling of the hard disk drive. Okay, because actually the hard disk drive is a very slow device, but as the multiple requests are given to the hard disk drive, and then these requests are stored in the request queue of the hard disk drive. So that means the hard disk drive can find multiple requests in this request queue. So each request has target sector for read, write, and erase, and then the location of this target sector is determined by this logical block address. But we can also reduce this seek time by controlling the order of request to the hard disk drive. Okay. So in this equation, we cannot change this part. This is the specification of the hard disk drive, but we can change this average seek time by changing the scheduling. That means the order of processed request inside of the hard disk drive. Okay. So when you study on the hard disk research, then we can also focus on the this mechanical part and then the density of the data inside of the hard disk drive. But in the software part, we can focus on the scheduling, data read scheduling, or data scheduling of this hard disk drive, because we can change this seek time by changing the scheduling of the hard disk request. So important point of this example is that access time is dominated by seek time, as I mentioned. Also, rotational latency. This rotational latency is determined by rotational speed. You cannot change. But seek time can be changed by scheduling. So compared to the DRAM access time is about tens nanosecond. So Disk access time is much slower. So in this slide, so we assume that the access time for double word is 4 nanosecond for SRAM, and then 60 nanosecond for DRAM. And then compared to the SRAM, it's about 40K times slower. The disk access time is 40K times slower, and then compared to the DRAM, it's about 25 kilo times slower. Okay, what that means much slower. Okay, so actually, as I mentioned, this structure of the data on this hard disk drive is not simple. It has some multiple hierarchy, structural hierarchy, platter, surface, track, and head. And then this number of like density or number of tracks per surface, so the number of platters are different by different hard disk drives. So that is the unique feature of the hard disk drive. So for example, if one hard disk drive is made by Western Digital and then another hard disk drive made by Seagate, but the dimension of this hard disk drive, the hard disk, that means the dimension of the platter can be different by different hard disk drives. So this architecture is different, then it's not easy to control this different hard disk drive by one operating system. So operating system just access the data on the hard disk drive, with the logical block numbers. And then these logical block numbers are translated into the location of the sector, like number of platter, number of surface, platter number, surface number, and track number and sector number on the track, like this. So the logical blocks should be translated into the physical location of the hard disk drive, okay, like this, surface, track, sectors. So that is performed by the firmware of the hard disk drive. Okay. Okay. So I will into here. So then let's see how the operating system communicates with the hard disk drive. So this is some typical system architecture of the host and the hard disk drive. It's a little bit old but the hard disk is the traditional storage system. For you, as you can see, as you know, the hard disk drive is connected to the host system via SATA interface. So it's an old interface, and then the SATA is usually managed by this Southbridge chip, but it's a mainboard chip. So it's connected to the I/O bus like this. So first, the host driver, the operating system, gives the request to this disk controller of the hard disk drive. And then if this request is given to the hard disk drive, and then the request is given to hard disk drive with the logical block address. Okay. And then this logical block address is translated the physical location of the hard disk drive, that means the data. And then the hard disk controller reads data from a surface of the disk and then transfer the read data to the main memory using DMA protocol. Okay. Then if this data transfer is done, then hard disk drive raises interrupt to the host device, so host CPU, and then interrupt is raised, then the host device can know that the data transfer is done from the hard disk drive. Then host system can read data from the main memory here. That's how the request is given to the hard disk drive, and then data is transferred, and then data transfer is notified by the interrupt. Okay, also, let's see some scheduling algorithm of the hard disk drive. So in the previous slide, I explained that the seek time can be changed by scheduling algorithm. Okay, because this seek time is determined by the location of the target sector and the location of the head, current location of head. So there are several scheduling algorithms like the FS, SSTF, scan, and C-scan. FCFS is a very simple scheduling algorithm. So first come, first served. First come, first served. So then means the in order processing. So that means that if the first request is firstly served by hard disk drive. So this scheduling algorithm does not consider the location of the current sector. So that means the no scheduling. But SSTF, the shortest seek time first, means that so there can be many requests in the request queue of the hard disk drive, and then each request may have the target sector. So based on these target sectors, we can know the minimum seek time for the next request. So for example, there are 10 requests in the hard disk request queue, and then the head of the hard disk drive is here. And then this request is the target sector. The target sector of this request is here, and then target sector of this request is here. So here. So the seek time for this request may be very long, but the seek time for this request here may be very short compared to this first request. So in this case, we can approximately calculate the minimum seek time for the multiple requests in the request queue. Then in order to reduce the seek time, we can first, the hard disk drive can first provide the data for this request. In order to reduce the seek time, that means the shortest seek time first. Okay. So with this SSTF scheduling, we can reduce we can minimize the seek time for the multiple requests. But what's the disadvantage? Potential starvation. So that means, so this is actually the hard disk drive does not know about the priority of the data request. So for example, this is the application running on the host system. And then actually this application requires this data, and then if this data is provided from the hard disk drive very quickly, then we can increase the performance of this application. So that means that this data can be the part of critical part. Okay. But hard disk drive does not know about the priority of the data request. So if we just apply the SSTF, the hard disk drive just provide the request that has the minimum seek time. So in that case, this block is not provided from the hard disk drive for a long time. So, but this is the critical data. The performance of this application can be degraded by this scheduling algorithm, because this critical data is not provided from the hard disk drive for a long time. Also, there can be potential starvation problem. So that means if the request is frequently given to the hard disk drive, but then this is the longest seek time. This request has the longest seek time. So, and then the incoming request has the shorter seek time compared to this first request. Then this first request will not be provided from the hard disk drive very long time, for a very long time, because only the shorter seek time, the request that has the shorter seek time will be provided hard disk drive earlier. Okay, so this is not serviced from the hard disk drive. So this is the potential problem of the hard disk drive. So this is SSTF scheduling algorithm. So interesting. So another scheduling algorithm is the scan. So scan is the, so this is, so I already explained that the arm of the hard disk drive moves like this. So scan means that firstly, the head of the hard disk drive moves to this direction. So this is the request queue of the hard disk drive. If the target sector is located here, okay, X, 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 and then if the head is moving to this direction, then this request is firstly served by hard disk drive, and then the head is moved to this direction. So this is the inner track. This is the inner track. This is the outer track. Then the head of the hard disk drive moves like this, like here, 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 here. And then if the target sector is here, then these sectors are firstly served, and then other requests are served for this direction. This is the scan scheduling. And C-scan is basically same to the scan, but it's one direction, like here, and then move to the other head to the inner track here, and then here, and then put here, here. So like this. So like time writer. So advantage of this scan scheduling is fairness. So if we apply the SSTF, then there can be fairness problem, like potential starvation. But if we use this scan scheduling, then the hard disk drive can also provide some fairness to the target request. So because the seek time can be changed by scheduling algorithms, and we can apply some various scheduling algorithms to improve the performance of hard disk drive. Okay, but when we consider this schedule task scheduling, and it's the same for other scheduling like operating system or real-time tasks, then we need to focus on the criticality of the data, also the fairness and overall performance. So actually the hard disk scheduling also should be considered for the criticality or fairness performance of entire systems. Okay, then so let's take a break for 10 minutes. Okay, this is so very long class, and so let's take a break for 10 minutes, and I will be back in 10 minutes. So do you have any questions? Yeah, okay, good. So let's take a break 10 minutes. So so I covered about I explained about the structure of the hard disk drive, but the rest of the class, I mean, so actually we will cover the hard disk drive only in this class because it's a traditional storage system. Then actually in this course we will focus on the architecture of the SSD. But hard disk drive is the traditional storage system, and then actually it's hard disk drives are still widely used in our computer systems and also in the server systems. So actually, the large server systems such as Google Data Center or Microsoft, Google, Amazon Data Center, hard disk drives are still the main storage devices because it's cheap. Even though the performance is very low, the price of the hard disk drive is just still cheap. So normal data. So that means if the data is not critical, such data is stored in the hard disk drive. It's very slow devices. But if the data is not accessed frequently, then we can store that type of data inside of hard disk drive. That's why the hard disk drives are still the main storage system in the server systems or server computer systems or cloud infrastructure. So actually Google reported the error rate of the hard disk drive because the Google uses the notch of hard disk drive. So they report that the hard disk drive is not reliable. Sometimes the hard disk drives are broken because of the mechanical part. Also, I have experienced the break of the hard disk drive, and then I was not able to restore my very important data inside of the hard disk drive. So that's the problem of the storage devices, actually. So, okay, let's continue. So we've learned about the hard disk drive, but as you can see, the performance of the hard disk drive is very low. The problem is that the modern big data applications require large amount of data from the storage. So the most of when the data is requested from the our from the storage, then data is firstly transferred to the main memory, and then the data is moved to the actually the register file, the level of cache and the register file inside of the core, and then the data is processed. But the data is frequently requested from the hard disk drive. The performance of overall application will be very low. So that's why we need the faster storage devices such as SSD. If we replace our hard disk drive with SSD, then we already know that the booting time, booting time of the operating system will be dramatically enhanced because the SSD speed is much higher than the hard disk drive. So in this example, the data access time of the hard disk drive is about 10 milliseconds. It's over 10 milliseconds, tens of milliseconds. But if we replace the hard disk drive with SSD, then the data access time is about the tens microsecond. So it's about 1,000 times faster than the hard disk drive. That's why. So we are using SSD for the critical data. Also, the feature of this, the SSD use the flash memory as the main storage media, and that means the mechanical part is removed from the storage system. So the flash memory is not reliable, and also we have limited number of arrays for the flash memory cells. So that means the flash memory is not permanent. But the reliability of the flash memory is, I think it's higher than that of HDD, hard disk drive, because there is no mechanical part. So let's compare the performance of storage system and the memory here. So it's somewhat out of the old data, so it's outdated data. So the bandwidth is about 50 to 100 megabytes per second. So bandwidth is actually the internal bandwidth is very low, not the HDD. And then also the interface of this HDD is also very low. And then if we use the SSD, the bandwidth is high. And actually, we can use the PCI Express for the storage interface for SSD. Then the bandwidth is much higher than the bandwidth of SATA. Okay, but cost is also very high. The size is outdated. So recently, the SSD size is also up to 2 terabytes. It's a very expensive SSD. So we can use up to 2 terabyte SSD for the personal use. And then for the HDD, the size is recently 8 terabyte to 16 terabyte recently for NAS, so network attached system. Network attached storage system. And then for DRAM, the DRAM is much faster than the SSD also. So about 1,000 times faster than SSD, so DRAM. Also bandwidth is very high. So actually the DRAM is directly connected to CPU. The DRAM bus is very wide, was fast. So DRAM bandwidth is about 10 gigabyte per second. Okay. And cost is also high. The size is limited. But so this is I captured this table from this site, the gaming PC builder. So actually, if I Google the fastest SSD currently, so so I found this website, the SSD ranking the fastest solid SSDs. So this table shows the recent data, so recent performance data of commercial SSD. So you can find, so this is the fastest SATA SSD, and then this is the fastest PCIe Generation 4 SSD. The sequential read bandwidth is about 500 megabyte per second. So if we compare this value, and then for PCIe SSD that use the NVMe protocol, the sequential read bandwidth is about 7 gigabyte per second. Sequential write it's lower than the read bandwidth, but it's about 5.3 gigabyte per second. But it is because the write latency, the write performance of the flash memory is lower than the read performance. It's about 10 times. The write latency is 10 times higher than the read latency. Okay. So recently, this is the, I think this is the maximum performance of the current SSD, commodity SSD. Okay. So we discussed about the hard disk drive. Then now let's see the architecture of SSD, the solid state drives. So unlike the hard disk drive that use the magnetic disks as storage media, SSDs use flash memory as main storage media. So it's flash memory. Why it's called flash memory? Flash. Because it's very fast. Oops. So actually the flash memory is, the property of the flash memory is very similar to EEPROM. So we can program EEPROM. So EEPROMs are usually used as some memory for CMOS BIOS of the computer system. It's called CMOS BIOS traditionally. So it's called flash memory because the speed of this flash memory is much faster than the speed of the EEPROM. So that's why the flash memory is called flash, has the name flash. Okay. One student ask a question. Okay. So actually the performance of the write of a flash memory is 10 times slower than, about 10 times, not exactly 10 times, about 10 times slower than the read latency of the flash memory. But the SSD is a system, not a flash memory. So actually SSD, there are multiple flash memory packages, and then also this flash memory is divided into some multiple architectural hierarchy, such as the disks. So this write number here is the write latency of the system, the SSD. So then this SSD also has DRAM buffer, and then some also SSD can you exploit the flash parallelism, like there are multiple packages or multiple chips, multiple dies inside of this flash memory that we can use some parallelism. And so these, in fact, these are all integrated into this performance value. So also the sequential write is not 10 times slower than the sequential read. Okay. So actually this sequential read bandwidth is limited by bandwidth of PCIe. Okay. So internal read bandwidth of this SSD may higher than this bandwidth of the storage interface. So NVMe SSD use the PCIe as the storage interface, but the bandwidth of this PCIe may be lower than the internal bandwidth of the flash memory. So, but for this write operation, we can apply many techniques such as buffering or write parallelism in the flash memory. So this value is not 10 times lower than this sequential read bandwidth. Usually this read bandwidth is limited by PCI bandwidth, and then this write bandwidth is influenced by the buffering, data buffering inside of the SSD. But there can be many other reasons for this sequential write bandwidth. Okay. So this slide summarized some typical feature of the flash memory. So flash memory is non-volatile memory, unlike DRAM. So that means the stored data is maintained even if the power is off to this SSD, the flash memory. So that's why we use flash memory as the main storage media of SSD. So non-volatile memory. And then flash memory has asymmetry read-write latency. So actually the write performance of the DRAM is lower than the read performance, but that is because of some interface issue, like for DRAM command issue. And then for read-write latency for DRAM is nearly same if we remove this protocol or some data transfer issue between read on the DRAM. But for the flash memory, read-write latency is asymmetry. That means the read is 10 times, usually, normally 10 times faster than the write performance, write speed. So in this example, the read latency is about the 10 microsecond. That is the latency of a flash memory, not SSD. 10 microsecond, and then the write latency is about the 100 microsecond. Micro. Okay. Then erase. Erase is very, very slow compared to read and write. So it is because of some data control. That means it is because of some mechanism of the flash memory. So I said so we will learn about some property of the flash memory next class. But I said the flash memory, actually the basic concept of the flash memory is very similar to EEPROM. EEPROM. So for EEPROM, in order to write the data, we need very high energy. So if we need a very high energy, then the latency will be very high. So usually for the flash memory, this flash memory requires the higher voltage for write operation. Also very high voltage for erase operation. That's why write is slower than the read operation. Also, the erasure is very, very slow compared to read and write. Also, read or erasure process requires a very high voltage. The erasure is performed at the uh, block granularity. So actually the read and writes are performed at a page granularity. It's a page, the size of the page is about 4 kilobyte to 16 kilobyte. And then block is composed of hundreds of pages. So the size of the block is larger than the size of page. But erasure should be performed at a block granularity because of this very high voltage for erase. And much slow. It's very slow. And then access granularity. Oh, I already mentioned. For read write, we can access the data in the flash memory at page granularity about 4 to 16 kilobyte. And then for the erasure should be performed at block granularity, like hundreds of pages. So these granularity are also asymmetric. So that means we need complex control or complex management for this flash memory. So how to describe the read, write, erasure, granularity are granularity is the same. So it's a sector-based. So access granularity for how to describe is a sector. Then it's same to the read, write, erase operations. But for the flash memory, it's different. For the read, write, it's a page granularity, and the eraser, the basic unit for erase is block. Also, it's very important characteristics. In place write is not supported. So what does that mean? Now, how to describe? Let's consider how to describe. Overwriting is possible. What does that mean? So some data is stored in the surface of the hard disk drive, as in a sector, and then for the write, for the data update, we can just write the new data to this sector, even though the data exists inside of this sector. But for the flash memory, in order to write a new data, we need to first erase the data inside of a target page. So just note that the basic granularity, access granularity for write is page. So we can write a new data to the target page. So because it's a access granularity page, but in order to write a new data, this page should be empty. Okay. Why is this important and critical for the SSD erase? The cost of erase very high for flash memory. read and write is fast, is very fast, but the cost of erase is very, very high. It's slow, and then erase should be performed at a block granularity. It's a large amount of, it's a large size. So actually, in order to support the in-place write, so target page, for the target page, the page is very similar to sector of the hard disk drive. Then we first, if the data exists in this target page, we first erase the page and then write new data to the target page. Erase will be very slow, and then it requires high energy. Also, erasure should be performed at block granularity. So, in order to support the in-place write, we first, in-place write, in the brute force, we first read whole data inside of the target block, then store this data in some temporary buffer, and then erase the entire block, and then update the target page with the new data, and then write the entire block with the buffered block data, and the updated data. It's inefficient. So because of this feature, this property, then we need to avoid erase operation. The erase is very slow. As a block granular, erase should be at block granularity. So in-place write is not supported, and then in order to increase the performance of the SSD, we need to address translation. Okay, because of the property of the storage media of SSD, we need to address translation. And then also another restriction is the limited number of writes per cell. So that means the available number of writes for the certain cell is the we can write the data to some target page with some limited number, limited numbers, limited times. Oh, sorry, limited times. So for example, if we write 1,000 times to the target page, then we cannot use this page anymore because the cell of this page is broken due to the high energy of the erase. So I mentioned in order to write the new data to the target page, we first need to erase the existing data. So actually the limited number of write is caused by this erase process. And then for the erase process, we need the very high energy for the flash memory cells. And then this high energy breaks the structure of the cell. So limited number of writes are allowed per cell. So because of this, we need to apply the wear leveling. Why do we apply the wear leveling? So we already know that for some data is frequently updated, but some data is not frequently updated. So for example, if we update some database data frequently, then this data is frequently updated. But if this data is stored in the same page and then updated 1,000 times, this page is, you cannot use this page. So that means the capacity of the SSD is reduced continuously. Also, if target page is fixed, then we cannot use this target page anymore. It is similar to the bad blocks in the hard disk drive. If the bad block is generated, so some part of the hard disk drive is broken, then we cannot use that part anymore. So it is marked as the bad block. Then operating system avoid the write to these bad blocks on the hard disk drive. So and then so if we write some several some about 1,000 times to the some target block, then we cannot use that target page. So we cannot use that page anymore. So and then the capacity of the SSD will be reduced. We use SSD for a long time. So in order to avoid this situation, we need SSD means wear leveling. Okay. So why address translation applied? Because of these features of flash memory. So let's think about the virtual to physical address translation in the virtual memory. So why do we apply the virtual memory to the computer system? So actually so there are many benefits of using virtual memory. So you know the process is it's not easy. It's very it's very difficult to manage the memory space by applications because application does not know the current situation of the computer system. So there are many benefits of using virtual memory, but what is the original reason to use the virtual memory? Why virtual memory was firstly invented? Because the memory size is limited. That means the size of the main memory is limited. The main memory is very expensive. And we can use the additional hard disk space as like the additional space for the main memory. But because of the performance, the frequently used data is stored in the main memory. And then if the data is not frequently used, then this type of data is kept in the hard disk drive. Then in order to support this operation, the virtual memory to physical virtual address to the physical address translation is applied in the computer system. So that is the original reason to apply the virtual memory in the computer systems. Okay. So what's the reason? Performance. In the flash memory, we can find the asymmetric performance between read and write. Also, another critical performance bottleneck is erase. Also, the asymmetry of the access granularity, and then many other reasons. And then, in order to hide this performance bottlenecks of flash memory, we apply address translation. And then this address translation is managed by system software of inside of SSD. That's right. That means firmware. So address translation is managed by firmware, not high performance bottleneck of flash memory. So the original purpose of using virtual memory is to hide some performance bottleneck from hard disk drive. Also, there can be many reasons, like main memory is so expensive, and then the size of the main memory is limited. And then, but it's because of this performance differences, we apply virtual memory to the computer system. Then the same mechanism is applied to the SSD. So SSD. So when we learned about the hard disk drive, the LBA, logical block address, is requested to the hard disk drive. Then hard disk drive translate this LBA information to some physical location, like platter number, surface number, sector numbers, trend number, and sector numbers. But this is some one-to-one mapping to the logical block address to physical location of the hard disk. The SSD also supports the LBA2 physical page address. But the flash memory is not a mechanical storage medium. That means it's a chip, like DRAM. So if the data is stored in a chip like DRAM, then we can actually directly convert this logical block address to the simple the architectural structure of the DRAM, the solid state memory. Because of the flash memory is the solid state memory, you can easily translate the logical block address to the physical structure of flash memory, physical architecture. But address translation of SSD has different purpose. The main purpose of address translation inside of SSD is caused by this unique feature of flash memory. It's performance asymmetric performance. Sorry. Then also the asymmetric access granularity. So another reason is the limited number of arrays or limited number of lines. So in order to support these in order to hide the performance bottlenecks, also in order to support the unique feature of flash memory, address translation is performed inside of SSD. That's why SSD is firmware is more complex than the system software of hard disk drive. So there are many research topics in the SSD research area because of these complex features, these unique features of flash memory. Okay. So let's see the inside of the SSD. So actually, in the first class, we learned about the typical architecture of I/O devices. It's the same. No, actually, I used the same figure in the first class. So not to show the example of typical I/O device architecture. So as you can see, so SSD has also its storage interface to the host system. So the SSD use the two different storage interface, such as SATA and PCI Express. And the SSD has its own system hardware, also it's a system software called firmware. SSD has embedded processor called the SSD processor, and then usually we use the ARM processor or real-time ARM processor as SSD processors. And then DRAM. SSD uses DRAM as the buffer space for data transfer, also the memory space for running SSD software, that means SSD's firmware. Okay, so if you see some specification of the SSD, commercial commodity SSD, you can find that some SSD show the size of the DRAM inside of the SSD, because if the DRAM size is large, then we can we can buffer the large amount of data from host system, so we can apply the more efficient as flash memory management software. Also, SSD has the NAND flash packages. So these chips, NAND flash chips, are used as the main storage media, the SSD. So let's see some architecture of the SSD briefly. So if you see the inside of the SSD is composed of some host interface part and then system software part, that is the firmware part. And these SSD processors are connected to the multiple NAND flash packages like this. So we can divide some internal architecture of the SSD like host interface part and then firmware part and flash memory part like this. And actually, this is some software part. Is a firmware part. Means system software, and then flash memory part is the storage media, the hardware. So SSD runs its firmware on using the embedded processor, and then the data is stored in this flash memory. This is the typical topology of the flash memory inside of the SSD. As you can see, multiple packages, so multiple chips are connected to the SSD processor. So if you see the inside of the high-performance server system, you can find that the CPU is here, and then many DIMMs are connected to the high-performance CPU like Xeon. So why do we use multiple DIMMs for this high-performance server system? So if the multiple DIMMs are connected to the CPU, then we can increase the performance. Also, we can increase the bandwidth, data bandwidth between CPU to main memory, between CPU and main memory. And then it's the same to the flash SSD. SSD also access the multiple packages, also that means multiple chips. And then the SSD can also employ the multiple channels for the flash memory. And then each channel can be connected to multiple packages, like multiple chips of flash memory. Why? With this parallelism, we can increase the bandwidth, the internal bandwidth of SSD. Also, we can increase the performance, data access performance between SSD processor and flash memory. So, and then these are also controlled by firmware running on the SSD processor. Like so, this firmware control performs some work of FTL and then buffering, data buffering, and IO scheduling and parallelism management, flash parallelism. Okay, so let's focus on the flash memory part. Okay, so like themes of the high performance server system, we can apply multiple channels to the flash memory. So, and on each channel, there is a flash memory controller. So like a DRAM controller inside of the CPU, the flash memory also needs the flash memory controller in order to access some request transaction and then some data transactions between embedded processor, SSD processor, and flash memory. So there can be multiple channels. Then each channel has its own flash memory controller. And then this channel is connected to some memory bus, flash memory bus. It's a single bus. And then on this single bus, multiple packages can be connected. So package means the chips. Multiple NAND flash chips can be connected to a single bus. So this package is called the way. So it's a channel, and then on the single channel, there can be multiple ways. And inside of a package, there can be multiple dies. So these multiple dies are very similar to the so dies has the independently working arrays. So in the memory, so in the DRAM chip, so there are multiple bank. There are multiple banks. So but these banks are working independently. So we can provide the parallelism with the multiple banks. It's the same to the NAND flash packages. So in a package, that means the single way or package, there can be multiple dies. So the dies shares this interface between the memory bus connected to the memory bus, but these dies work in parallel. The dies work in parallel. Okay, it's very similar to the concept of the bank and plane. So there can be multiple planes inside of a die, a single die, but this plane is used for increase the width of the data transfer. So actually plane works, a multiple plane work simultaneously, and then this multiple plane share the same word line. So that means we use these multiple planes to increase the memory, the size of width of the flash memory bus inside of a die. Okay. So like hierarchy of the hard disk, the flash memory has also some architectural hierarchy such as channel, way, die, and plane. Okay. Also, like DRAM, the performance of accessing sequence for this channel, way, die, frame is also influences the performance of flash memory. So these are also the research topic of the flash memory. Okay. So I will explain more about the parallelism in flash memory in the next class. So I covered some brief architecture of the SSD, like some software part, it's an interface, and some firmware part of the SSD, and then also I briefly mentioned some topology of flash memory inside of the SSD, and then we also learned that the SSD has some architectural hierarchy. Flash memory has the architectural hierarchy such as channels, way, dies, and planes. Like DRAM, it's very similar to DRAM because it's a solid state memory. Then, based on this topology, we can apply some different scheduling for the flash memory accesses, and then this can be also some research topics. So I will stop here. Also, very long class today. Do you have any questions? Okay. Thank you very much for your attention and your time. Also, I will. So actually, I'm posting my lecture videos or lecture slides and lecture video and then some reading materials on the Piazza resources tab on Piazza. So please find the tutorials on the Piazza. So, and then you can visit this resources tab of Piazza by clicking resources on the left panel of a Blackboard. Okay. Okay. Thank you for your attention, and then see you in the next time.